So the course has 3 parts. The first was a simple problem by simple methods. The second part are general issues that crop up nearly always, and we're in the middle of that. And then the third part are some much more specialized topics which may never affect you. The second part has several lectures on discretization, turning a continuous differential equation into a discrete finite problem for a computer. And then there's time integration and linear algebra. So last time I gave a more sophisticated version of finite differences where we could look at some higher derivatives and then higher order accuracy, not just second order or not just first order in some cases, but increasing the accuracy of the evaluation of derivatives. When you go to higher order, like fourth order, you tend to end up with wide numerical molecules, and there's a little trick that you can sometimes play, and I wrote it out in detail for the Poisson equation, which is such an important equation, and also told you the answer for the diffusion equation, where you can somehow find out what the errors are in terms of the given information, and then push the question to a higher accuracy, but maintaining a compact form. So by having a compact form, there's no complication when you get near the boundary of having to access points beyond the boundary. Okay, then there's a important issue that the governing equations have the advective derivative u dot grad u, dot grad temperature, moving with the fluid, and that is about information flowing from upstream to downstream. And then when you're trying to work out derivatives, it might be wise to only use upstream information and not try and predict what's happening in terms of what is happening in the future. Okay. There was a little quick discussion about non-Cartesian grids, because we do use polar coordinates and other things, and the staggered grids, and also an issue of, are you going to have a conservative system? So I wrote out what was needed to for a global conservation of momentum. So what numerically, you're not, in solving the momentum equation, you're not doing a perfect job at each point, but you can make sure you do an exact job on the whole domain. And that's so that I get the total force is 0. In this problem, there is no net momentum in the interior. Agreed things are moving to the right, but there's a compensating amount moving to the left. So there's no net momentum at the beginning or at the end. And therefore, at all times, it's necessary that the forces added up over all 4 surfaces equals 0. And most numerical schemes will be approximately 0 to second order 0. Sometimes you would like it to be exactly 0. I think probably I don't always need to exactly conserve momentum. You may want to exactly conserve energy. Otherwise, you just lose energy and peter out to nothing if you're doing a long-term calculation. Okay, so today there's 2 lectures on finite differences, finite elements rather. So finite elements is a way of representing the unknowns for putting into a partial differential equation. Is very good for most engineering problems which involve a complex geometry. The finite differences are great if your world is a square, but no engineering problem is a square. So they're very good for complex geometries. All you have to be able to do is to triangulate the domain, and that's actually not so simple. So you have to find some method of triangulating the domain. Sometimes you can divide the domain into rectangles, but not for really complex geometries. It tends to be that you have to divide the domain into triangles. It's exceptionally good. It was originally designed in the 50s for use on elliptic problems, so solving Poisson problems. It works quite well for parabolic equations, for diffusion equations, and it is not good, although very few people recognize this, for hyperbolic equations. So for our u dot grad u term, it doesn't do a very good job because it does do quite a lot of up, downstream, backwards influence. Finite elements are quite good on accuracy. They tend to be slightly more accurate than you think they are. That's good. And they tend to be a conservative system. So you get a global conservative property automatically, which is good. Okay, they are poor for various reasons. One is you've got triangles in a horrible mess. On a Cartesian grid, you know who's next to you. They're all ordered. It's a nice structure. When you've got these triangles all over the place, particularly if you introduce a new triangle when you want a little more resolution halfway through the calculation, you're dealing with an unstructured grid, and so working out who your neighbor is a serious issue. There's no really efficient Poisson solver. I suppose domain decomposition is quite good, but having fast Poisson solvers becomes a problem. And then when you've got your results, it's very difficult to see what the results are because you've got values all over the place, and you'd like to have a nice contour plot. So actually visualizing the data is an issue. It's connected with the difficulty in programming on an unstructured grid. So the answer is don't do it yourself. Do use a finite element package. So I'm going to tell you what's under the lid, what's happening in these finite element packages, but with this knowledge, don't use it. Or don't use it to program yourself, please, because it's a horrible problem, and I've done it several times. Do use some package, of which there are many. But it's a good idea if you're using a package to understand what the package is doing. So that's what these 2 lectures are doing, is explaining what the package is doing. And particularly at the end, when we go to applying it to the Navier-Stokes equations, there are some difficult issues which they fudge a bit. And you might have to know about what they're doing there. Yes? I've got, say, a pack here of the immediate one. So we're still lecture 2. That was lecture 1, the morning, this current lecture. So has everyone got a copy? So actually, I added that last night. So can you add it to your notes? It's not on the handout. This last line, this warning. That's very important. Okay, the finite element approach uses two new ideas. The first one is that we represent the unknown functions as functions. So in finite differencing, we were thinking of representing the unknown functions as values at grid points. So we just have data points. The idea in a finite elements is you represent the unknown by a function, a combination of lots of functions. But because you've got a function, you could work out the value at any point, not at particular grid points, not at the vertices of triangles. You can find out in the interior. And then the second thing is you convert your governing equations into something which I'm going to call the weak formulation. I may not explain quite what that is until the second lecture this morning, but think of it as a variational statement. So equivalent to the Poisson problem, there is a variational statement, and we use that, and it has some advantages. Very briefly at the moment, that you can substitute in a function which doesn't have two derivatives. We're trying to solve Laplace's equation, which is about two derivatives of x and two derivatives in y, but you can substitute a function which only has one derivative. And you can approximate a curve by linear lines, and that's what we're doing, and it sounds wrong. But if you use the weak formulation of the governing equations, you're allowed to do it. You're not allowed to do it in the governing equation. Okay, so we'll get to more of that later. So the first thing we've got to handle is the representation. And we'll do one dimension, then we'll do two dimensions, and we'll go through a sequence of more and more sophisticated representations. So the easiest, simplest way of representing a function, the curve, is by a series, as a histogram of constant values in intervals. The intervals don't have to be equispaced. That's what the advantage of finite elements. You can crowd elements where something interesting is happening, where you want to have a good resolution. So there's no restriction of thinking about. You don't want to think about equispaced or anything like that. So on this one-dimensional example, these points are just along the interval, usefully chosen. And although you could say that the function is the spot value, say at one end or in the middle, you should get away from the idea you should now think not that as a data point, but it's a parameter that specifies the function. Say more of that in a minute. So one representation is constant elements, and then of course we could have linear elements where it's very difficult to see the difference between my linear line and my curve because they're too close together. There is a difference, not in this projection. So again, this is on an interval between 2 points, and you can see at x equals I, this term vanishes, so that we have fi, and at x equals x equals xi minus 1, at the beginning of the interval, this term vanishes, and we're looking at the value. So it happens to be the value, but these are two parameters that specify a linear function. So we can then go up. I'm going to now go from constant, linear, up to quadratic, and then on to cubic. And that last formula has got a lot of mess in it. So the best thing to do is to transform the interval that you're concentrating on to a transform variable which varies from 0 to 1. So xi equals 0, we're at xi minus 1, and at xi equals 1, we are at xi. Then I can express the function in terms of xi. So I'm now having a quadratic, so there are quadratic expressions in terms of xi, which of course are quadratic expressions in terms of x. And there are 3 parameters in a quadratic, and I've chosen the expression there to actually be the value of the function at xi equals 0. If you put xi equals 0, this is 1, this is 0, and that is 0. So this function is actually equal to fi minus 1 at xi equals 0. At the other end, at xi equals 1, that vanishes, and it's fi. And in the middle, at xi equals a half, this vanishes, and this is a half. Sorry, this is a half times 4 is 1. So it's equal to f at I minus a half. Okay. So this is a quadratic, it's nice. So we're representing the unknown by a nice smooth quadratic in the interior. And if we use the same value fi minus 1 in the interval before, and the same value fi in the interval next along, we've got a continuous function, except the derivative's not continuous at the ends of the intervals. So it's better, but it's not perfect. And then this is a cubic representation. So for a cubic, there are 4 terms. And I've chosen to write it out in terms of what is the value of the function at the beginning of the interval and the end of the interval. So this is the value of the function at xi equals 0, and this is the value of the function at xi equals 1. And I've got what is the derivative at the beginning of the interval and what is the derivative at the end of the interval. So now this function has 4 parameters for this interval, and different 4 parameters at the previous interval. If we choose the value of the function and the derivative to be the same at the interval before, and the same as the interval afterwards, we end up with a representation over the whole interval which is continuous, and its derivative is continuous. But the second derivative, which is nice in every single interval, is not continuous at the joining points. However, there's another subject, not finite elements, called splines, where you require the values of the derivatives, which you probably don't know, to be such that the second derivative is continuous. I'll talk about splines later on when I want to talk about representations of surfaces as a special topic. So forget that remark, that's not to do with finite elements. Okay, in all of the cases, we should now start thinking as writing the function as being a sum of some amplitudes, sometimes the value at the end of the interval, sometimes this amplitude isn't the value of the function at the end of the interval, but the value of the derivative at the end of the interval. So there are some parameters that specify the functions, sometimes the value of a function at a particular point, sometimes a derivative, sometimes something totally different. So we write the function as some amplitudes multiplied by some basis functions, which were those linear functions, quadratic functions, cubic functions. And those functions associated with the basis function associated with a particular amplitude tend to be 0 most everywhere, and it's just a couple of elements where they're non-zero. So it's a very localized representation. This function is one particular basis function will be vanish in most elements, but be non-zero in just a couple. Okay, and the basis functions for the constant elements are exactly 0 everywhere, except in one element where they're equal to 1. For the linear interval, linear representations, the basis functions, again, vanish outside 2 intervals, outside 2 elements, and then we have a linear variation in each element. But they vanish mostly. When it comes to the cubic elements, I've skipped over quadratic, there are essentially 2 basis functions. There's a basis function, well, all the 2 basis functions vanish mostly and are non-zero in 2 elements. And one basis function is equal to 1 in the middle and has 0 derivative at the beginning, 0 derivative at the middle, and 0 derivative at the end. And the other basis function, it vanishes before and after the 2 elements, has 0 value and 0 derivative at the beginning, 0 value and 0 derivative at the end, and in the middle it has 0 value but a slope of 1. So we could use these twiddle basis functions and the basis functions in combination. So we call them now both basis functions phi, and then we multiply by amplitudes. Half the amplitudes are the value of the function at a join between 2 elements, 2 intervals, and half of the amplitudes are the derivatives at the end of the interval, at the end of an element. Okay, so that's one dimension. And then the same thing happens in 2 dimensions. We could have constants over a triangle. I'm thinking of triangles, I think, because we mostly use triangles. Just occasionally do we use rectangles. And rectangles don't quite work so nicely. The linear elements, what we need is come up with a function which is linear and vanishes at 2 points. So my linear function 1, 2 vanishes at x equals 1 and vector x equals 1. So x, it vanishes at x1, y1. It vanishes at x2, y2. And at the other number, 3, at x3, y3, it is equal to 1. Okay? So let's test this out. At x equals x1, the first term vanishes, and at y equals y1, the second term vanishes. So this vanishes there, and it also vanishes, more complicated, at x equals x2 and y equals y2. So at x equals x2 and y equals y2, then that product cancels that product. And then at x equals x3 and y equals x3, the numerator is equal to the denominator. Do we agree? So now I've got a linear function, and there are 2 other functions. There's a little l with 2, 3, and a little l with 3, 1, which are each in turn are equal to 1 at 1 vertex and 0 at 2 vertices. So then, the general representation, or a linear representation of the function over the triangle can be written as a combination of these three basis functions. Well, they're not basis functions yet. What is the basis function in one triangle? We've got to think about the other triangles nearby. And multiply by 3 amplitudes, which happen to be the values of the function at the vertices. That's the linear function. So okay. The word it says representation is continuous over the domain. It's only continuous over this triangle. Or it will be continuous over the whole domain when I put them all together. Okay, the quadratic elements, I use those linear function. I have a linear function. If I square a linear function or form a product of 2 linear functions, I get a quadratic function. Okay, so I can take the linear function which vanishes at x2 and x3 and twice the linear function that vanishes at x2, x3 minus 1, and then I construct something which is, oh dear, what on earth have I got here? That's okay. I think that vanishes at 2 and 3 and is equal to is also equal to 1 at the vertex. At vertex. At vertex 1, this is 1 and this is 1, so the product is 1. So this is the value of the function at 1. So the first 3 terms are quadratics, and they vanish at the 2 vertices that they've got the subscripts at 2, 3, at 3, 1, and at 1, 2, and they're equal to 1 at the vertex, the index not mentioned. And then the bottom line, which is a product 1, 2, and 3, 1, that means that that product has to vanish at x equals 1, 2, and 3, and 1, so it vanishes at 1, 2, all 3 vertices. However, at the middle points, it is not 0. So I think this vanishes along the line from x1 to x2. This vanishes along the line from x3 to x1. But the line from x2 to x3, this doesn't vanish. And halfway along, both of them, because they're linear, are equal to a half. So if I multiply by 4, they're equal to 1 in the midpoint. between 2 and 3. Try that? Sorry, could you see over there? Let me redo that. So this function vanishes along the line 1, 2. This vanishes along the line 3, 1. But it doesn't tell you what's happening along the line 2, 3. And at the midpoint along 2, 3, this is a half, because it's linear. And this is a half, because it's halfway along. And half times 4 is 1. So this curved function here vanishes along 2 sides, and it's quadratic, and it's at the midpoint along, it's equal to 1. And here there's I don't understand these. These are quadratic surfaces which are doing what I would like them to do. This is the first 3. They are equal to 1 somewhere and vanish along the opposite line, and are quadratic between. This is the bottom line, which vanish on 2 lines and are equal to 1 on the midpoint. Okay, if I jump the quadratic representation, so the cubic representation, a cubic in 2 dimensions has 10, is that right? Yes, has 10 constants. Should we count it? It could take a long time. So there's one constant value. The gradient in 2 dimensions got 2 values. The quadratic term has 2 x derivatives, 2 y derivatives, but an xy derivative has 3 terms. And the cubic term pretty obviously has 4. So there are 10 unknowns, 10 constants in a 2-dimensional cubic. And I can use those to be so that I can fit with the values of the function and the derivatives, the x and y derivatives, at all 3 vertices. So this is 1 piece of information, 2 pieces of information, 3 pieces of information at 3 vertices is 9 constants have been used up on this cubic, and there's 1 left over. And what we tend to do is, with the last term, is to vanish at all of the vertices, and derivatives vanish at all the vertices, and equal to 1 right in the middle. And that has a curious name. It's called a bubble function. It just pops up in the middle, but there's nothing around the sides. Now, if you use this as a representation, because we're getting the right values and the right derivatives at each of the vertices, then it means that the function, if we use it for one triangle, the same values and derivatives for the next triangle, then it means that the function is continuous along the join, and the tangential derivative is continuous. Unfortunately, the normal derivative isn't continuous. And what's worse is at the vertex, where probably there are 5 triangles joining, you get the value the same, but the derivative has a very unhappy time. Do I believe? That might be true. As I said, you can't always believe everything I say. Think about it. Okay, in all of these cases, for the linear, quadratic, and cubic elements, we can write the function as some amplitude, which may or may not be a spot value of the function, times a basis function. And we've talked about the basis function in one triangle, but we have to remember, say, the spot value joins up with all the triangles associated with that vertex. So in the case of linear elements, the basis function will be non-zero at only one vertex, but that vertex will be in several triangles, and in each of those triangles it vanishes on the other 2 vertices. So this basis function is a pyramid with linear sides, and it may be 5-sided or 6-sided or 3-sided. It depends how many triangles meet at the vertex. Okay, the fact that the basis function vanishes at most places, and it's just at a few triangles near one vertex, that it's non-zero, is very good. It's a local representation, and that's very good for partial differential equations, because partial differential equations are about gradients, so they're about how does a function vary locally. Partial differential equations equal local variations equals a local representation. It all matches nicely. Okay, so I've talked in 2 dimensions about triangles. The rectangles is pretty obvious what you can do with a constant. You can't, there is no linear function that fits 4 points in 2 dimensions. So you can't have a linear representation. But there are things called bilinear. So it is linear in one variable and linear in the other variable. And if you make a product of a linear and a linear, it is a quadratic, but it's not the general quadratic. So there is no xi squared or no eta squared there. There's only xi eta. So it's a restricted quadratic. And this is a linear function which takes the spot values f1 at xi equals 1 and eta equals 1. This takes the spot value f4 at xi equals 1 and eta equals, no, at xi equals 0 and eta equals 0, where the others all vanish, etc. That's continuous over that rectangle, and it would be continuous if you use those same spot values at the vertices, continuous into the next domain, but the derivatives wouldn't be. Okay. There is that's a bilinear, there's a biquadratic, which would be a sum of quadratics in psi and quadratics in eta. So there would be a quartic term, which would be psi squared, eta squared, but there wouldn't be any other quartic terms. And you can rig it so it takes the spot values at the vertices and at the midpoints with that extra freedom. And that has, if you use the same values at the adjacent rectangle, you have a representation over the whole domain, which is continuous and has continuous tangential derivatives, but not continuous normal derivatives. Right. So for the Poisson problem, there is a variational statement. So our Poisson problem is del squared some unknown function is equal to a given rho, and the unknown function is equal to a given g on the surface. And there is what's called a Rayleigh-Ritz, is also called other things, variational formulation, which says the function f, which satisfies the boundary condition, f equals g on the boundary, and minimizes this integral, happens to solve the Poisson problem. So there's a calculus of variations. So 1. Have you come across the calculus of variations? And 2, even if you've not, do you know this? No? Okay. Well, I don't think I can give a lesson on the calculus variation in 2 minutes. Do you really want this? Would you like to know? Doesn't matter too much. We're going to use it, but you might be reassured if you've seen why it works. So I have an integral of a half grad f squared plus rho f. And I'll put a dv. And I'm going to take f to equal 0 plus a little f, delta f. And that's small. So I'm going to put into this expression something plus a small amount. And I'm going to work, what I would like is that this integral is going to be a value corresponding to f naught plus a small amount. And if I'm at the maximum value or the minimum value or some stationary value, the small amount will have a coefficient of 0, and I will have then a quadratic amount only. So, right, I put that in. So the first bit, no difficulty. So that's when delta is 0. And then I have a gradient of f0 times a gradient of delta f plus a rho and delta f dv plus delta squared. And the delta squared is quite easy to write down. Right, so this is the value. So if I look at delta I, because I don't want to keep on writing this bit down, I can integrate this by parts. So if I integrate by parts, I will get, so that's the divergence theorem. So I want to make this the divergence of something. So this is going to be the divergence of, get it right the way around, and then minus del squared f naught times delta f. Okay, the volume integral of the divergence will give me a surface integral of the f naught by dn times delta f, the surface, and then I'm going to get plus an integral of minus del squared f naught plus rho times delta f dv. Can you see the next line down? Right. Now, on the boundary, f naught is equal to g, and if my function f naught plus delta f is also equal to g, then delta f has to be 0 on the boundary. I've spent all my boundary condition g on f naught, so delta f has to be 0. On the boundary, this is 0. Then I've got an integral of something times delta f, and I would really like this delta I. I'd like this integral to vanish for whatever delta f is. And so I could think of the delta f, it could be any function as long as it's nice enough to be differentiated, as being a highly localized Gaussian around some arbitrary point. So if it's a highly localized object around some point, around that region, this is roughly constant at that point, so I can take this outside the integral, and then I'd get an integral of delta f. And so if I wanted that to vanish, this better vanish at that point. So what I'm saying is, I'd like delta I is equal to 0 for all delta f if minus del squared f naught plus rho is equal to 0 everywhere. Okay, so just to repeat that last interval, if this integrand, this bracketed term, was not 0 at some point, then I would choose out of my arbitrary possible delta f's, a delta f which is a localized Gaussian round that point. And so that this integral would be, only can get values from around that point. And because this is a smooth variation around the localized point, I can take that outside as roughly constant. And then I'll arrange the integral of a localized Gaussian is not 0. So I'd get a non-zero unless that bracket vanished at that point. So you don't know this. Very good. Do you know it now? Okay, so back to the slides here. That's called in my area, but it's called in different things in different areas, the Rayleigh-Ritz principle. And I can solve that partial differential equation if I look at that integral and try and find the stationary values. It would be, in fact, the minimum for this, because you can quite easily persuade yourself that the delta squared terms is going to be the gradient of delta f squared, which is a positive amount. This is, while I can get this term to vanish, this is always going to be positive. And so at the optimum state, this is a minimum. So the function that minimizes that integral solves the Poisson problem. So that we're not going to solve the Poisson problem, we're going to minimize that integral. So what happens is we substitute our finite element representation into that integral. So there's the quadratic term, a half grad phi squared. So the amplitudes, they're constant, they're just parameters. So we take them outside and we have the product of two basis functions, the gradient of two basis functions. And then the third term, this part here, we take the amplitudes outside and we have rho phi I. We have a sum over the contributions from the many different phi's, basis functions. So that is the integral. And now I'd like to find what is the maximum of that I with respect to the variable parameters. We can change the values of the parameters. So that this is a very simple quadratic maximization, minimization problem. So if I minimize with respect to varying the parameters fi, I get, differentiating this with respect to fi, I get a linear term in fi, and differentiating that with respect to fi, I just get a single term. It's much easier if I write out. Okay, so I've defined here the integral of the product of two basis functions as being it's called a global stiffness matrix, and then the integral of a basis function times the given rho, that we're solving del squared phi equals rho, is called a forcing term, rho I. And if you minimize with respect to varying the parameters, you get kf plus rho is equal to 0. So it's just ax equals b, linear problem to solve. And if you choose your parameters to satisfy this equation, then it means that the sum of these fi's times the gradients of the the sum of the fi times the phi, which is the function, satisfies this. And that's an interesting remark. Does it say so here? Yeah. What this is saying, by picking up the Fi, so there are Fj's there, multiplying by the phi's. And what I'm saying is that the equation, because this is really del squared F and rho, I'm saying that the governing equation, del squared F is equal to rho, has zero component in all of the directions of the basis functions. So I'm living in a vector space, and the possible variations are given by the directions of each in basis function. And I'm saying the components of the equation, the residual in the equation, has zero components in the directions that I can talk about, which are the basis functions. And this is, as I hinted a bit earlier, this is a weak formulation. I can put in basis functions like those linear variations, which have one derivative. So my basis functions phi have one derivative, but they can't do del squared phi, because they have, well, del squared phi is actually a delta function around the perimeter. So they're not C2. They don't have two derivatives. Okay, so that's in general. Let's look at the Poisson equation in one dimension and then in two dimensions. So the Poisson equation in one dimension is two derivatives is equal to rho. We're given rho, it's on an interval, and we're given the values at the ends of the interval. It's the one-dimensional version. And I'm going to divide it initially into equal segments. I said that finite elements don't have to be equal. Let me do it into equal ones. Then our basis functions are these, for linear elements, for linear finite elements, the basis functions are just triangles. They vanish and then are non-zero in two intervals and then vanish again. And there's two special ones at the end which are only half a triangle. They're the basis functions. We build the boundary conditions in by saying that we represent our function over the whole domain, including the boundaries, as being a times the first basis function plus b times the last basis function. That means this function satisfies the boundary conditions. And then there are some unknown amplitudes which actually happen to be the spot values in between, but this is a representation of every value of x, not just the grid points. So I have to work out this stiffness matrix, and the stiffness matrix, that's the integral over the domain of the product of the gradients of two basis functions. The basis functions for that triangle, if the width of the triangle is h, is essentially plus 1 upon h or minus 1 upon h. So this stiffness function will be if I is equal to j, it's the same function, and it's got both positive up and a negative down. So that's going to be 1 upon h squared plus, now although it's minus 1 upon h, but it's squared, so it's 1 upon h squared. And then we're integrating, so we have to multiply by the width of the interval in each case, so it's an h. So we get 2 upon h. On the other hand, if we have a triangle up and we have a triangle in the, if we're just one interval along, then we will multiply an up by a down. So we're going to get a 1 upon h squared and a, that's up for you, isn't it? 1 upon h squared, and then down for you is minus 1 upon h squared. So we get 1 upon h and minus 1 upon h. Multiplied is minus 1 upon h squared, multiplied by the width that we're integrating over is h. So I get minus 1 upon h. And in the case when I is different from, when j is different from I is different by j, by more than 1, they're non-overlapping triangles. So the product of grad phi I and grad phi j is 0. Okay? And then this is effectively, so we have a linear variation over a triangle, and I'm going to say that that is the value of the function in the middle somehow, being slightly vague. So the governing equation turns out to be this. And that's pretty familiar. It's the same as finite differencing. So while we had the FIs as being parameters, actually they were the values at the ends of the intervals. So then this is exactly the governing equation we get is exactly the same as for finite differences. So it's rather nice that finite elements gives finite differences. There'd be an issue if it didn't. And actually, if I did a slightly better job at the integral, with a triangular function here, it isn't quite the spot value. There's a 1 upon... That can't be right. It has to be 1 upon h squared. You may want to try and derive that. Perhaps there's a... perhaps, is there... I think there's an h there missing. That would be better. So there's an error with an h there missing. Which means I might be on... And it turns out that this term here is just what you want to get in finite difference language, a compact higher order accurate question. So we had a compact higher order delta x fourth accurate finite difference formulation. And if you were to have evaluated these, this forcing term to the higher accuracy, then you end up getting the spot values at fourth order accurate. However, you've only got a linear interpolation between the spot values with this representation. So there are quadratic errors, differences between the true function and the linear interpolation. But you got the m values better than you should have done. That's very typical of finite elements. You get something better than you should have done, but then it's not quite. Okay. And if I made that calculation for equispaced intervals. If you don't have equispace, but if each interval has a different length, and you follow through all the calculations, you find that you get this version. So instead of being the spot value in front, spot value behind, and two values, twice the spot value at the middle point, you end up with that formulation, those numbers with slight biases because of the different h's, and that turns out to be in finite difference equations. If we'd have made a conservative finite difference scheme, we would have got this equation. So it's telling you that finite elements, when we always use non-equispaced things, is a conservative system. Gives you a globally conservative formulation. Oh, I got to the end. Don't have to worry about saying anything more. Okay, so that's the first part of finite elements. We'll then, in an hour's time, finish finite elements, where we'll look at the diffusion equation, and then we'll look at the Navier-Stokes equations. Are there any questions? Yes?
So why is it that we are allowed to use the linear approximation only after the recombination and not writing that in the equation directly?
Right, I'm glad that you are worried that I'm solving del squared phi equals rho, which requires second derivatives with approximation to this curve function by linear segments. I can always approximate a curve by linear segments, but if I were to work out the second derivatives, they would be delta functions at the joins. And you should be alarmed by that. You're quite right. But that's the whole point about weak formulations, is you show that the partial differential equation is equivalent to the Rayleigh-Ritz, the variational statement, and in the variational statement, you are allowed to have linear functions, because I just want the gradient of the function, and for a linear function that exists. So it's quite happy to use a linear, piecewise linear approximation in the variational statement. Right. So if you want to be a pure mathematician, now what you have to do is to show, as I increase the resolution, the linear approximation converges to something. Does it converge as I increase the resolution? Having proved that the process converges as you increase the resolution, you have to show that the limit that you're tending to is nice. Equals has two derivatives, which any approximation didn't have. And then when you've proved it's nice, called regular in technical terms, you have to show that the regularized solution satisfies the partial differential equation. It's quite a lot of hard work, which would... So I could spend all next week doing that, but I have to erect a whole apparatus of functional analysis to be able to prove that sort of thing. Okay? We're not going to do that. Okay, do I get a break? Fine.